Okay, welcome everyone to today's Bosonic Learning Theory Winter School. And it is great pleasure to me to introduce Filippo Girardi today. He will be giving a lecture titled Gaussianity Testing of Bosonic Quantum State. And welcome.
Thank you so much, Jinseo, for the introduction, and nice to meet you all. Today I'm going to introduce, the task of property testing, and in particular, testing of Gaussianity in the setting of infinite dimensional systems. So I will focus on the results of a work. Oh, with co-authors Freek Witteveen, Francesco Annamele, Lennart Wittel, Salvatore Oliviero, David Gross, and Michael Walter. So if you have any question, feel free to stop me, to ask. Don't be shy. I would prefer to mm, give you a clear introduction to the topic rather than to finishing all my 100 slides that I prepared. So if we don't manage to finish all the things that I prepared, it's not a problem. I would prefer you to let me know if I'm too fast, too slow, if I'm missing something, if you have any doubt. I hope you will enjoy this topic. So, according to what Junso told me, you are already expert of infinite dimensional systems, so I will not give you such a detailed introduction to bosonic system, and also to Gaussian state. You already had some lectures about this topic. I will focus rather on the setting of property testing. So let's start with a practical example. Suppose that you just bought state preparation device which is supposed to produce uh, IID copies of a given Gaussian state, but you don't know which one, and you want to test whether this device is working properly or not. How would you proceed? Well, you should make a test such that with failure probability at most delta, this test tells you if the state which is tested is Gaussian or not. So the question, apart from how we could design this test in practice, is also more fundamental. How long will it take this procedure? Shall we uh, make it before the warranty expiration of this device, or shall we wait for years and years? In other words, what is the sample complexity of this task? How many copies of the state that we are testing are needed in terms of the system size? And you know that the system size for infinite dimensional system is the number of modes. Uh, and also the energy is a measure of size of the system. So how will they scale? How will n scale with respect to them? So let's start from the beginning. What's property testing? In general, we want to make a partition of our set of states. Ah, by the way, if you, I will go a bit fast on some details, but I will share the slides with you. So, I mean, you don't need to take notes if you want directly the slides. I will share them with Junseo. So we are partitioning our set of states into two subsets, one having a property and one mm, not having it. And we want our test to accept with high probability the states which are in this subset. And I say subset and not subspace because in general it might not be a subspace. And to reject the states which are outside. Um, So how do you do that? Well, simply design a POVM, first element accept, second element reject. And the request of the probability is just that uh, the acceptance probability should be smaller than delta when you take a state which does not have this property and it should be larger than 1 minus delta if the state has the property. So I will give you a fundamental example. I will say a paradigmatic example from the classical case, which was extensively studied in the literature, and it's called identity testing. So suppose that you have a known reference probability distribution Q, uh, and you want to sample IID copies of a random variable X in order to decide whether the probability distribution of X is Q or is another P, any other P. And in the end, you want to say yes, it is Q, or no, it is not Q. So, what could the problem be here, according to you? I mean, do you want to guess what's the problem here? Is there someone who has any idea about? So, feel free to react. It's not a problem if you don't need to give necessarily right answer, but I mean, it should be. I don't know, natural to ask whether we can really define a sample complexity if, in principle, we could consider arbitrarily close probability distributions P to Q, because then, in principle, you would need an unlimited number of samples to exactly uh, understand whether you are observing P or Q. So, what you will see also in the generic setting of property testing is that we need to introduce a gray area. And gray area in this case is a ball or radius epsilon according to the total variation distance. So the test, well, there are two ways to phrase the property testing in this case. One is, okay, you have the promise that your random variables are distributed either according to Q or according to a P, which is at least epsilon far in trace distance, or in total variation, the classical case. And then you have to accept Q and reject P. But you see, doesn't sound so natural to assume a promise, because if you are observing a physical phenomenon, and you want to test its property in order to develop your theory, um, you don't have, in principle, promises. So, a way that I prefer to phrase this problem is that, okay, you want to design a test which accepts Q when you have a probability distribution which is in the gray area. You don't care so much if the answer is yes or no. You just care that about the fact that it must be no when you're outside the gray area. And why? Well, because if it's not Q and it is in the gray area, then in case you get as an outcome no, then I mean it's fine. It's not Q, so it's fine to reject it. But if you get the yes, and you choose you already chose epsilon to be small enough, well, in the end it's not so far from Q, so it's approximately Q. So in principle, for some application it could be fine. um, so the sample complexity of this problem is well known. It can be also stated in terms particular of the specific Q that you are studying. And just to let you understand how it could be, the basic example is to take the uniform distribution, and here you can see X is the space on which these random variables take value. So in this case, in uniformity testing, you see that the number of copy has a strong dependence on the system size, and that's why we could say that in this case, testing is hard. The same problem was also studied for the quantum setting. So especially the finite dimensional setting. There are two works. The first one regarding identity testing with the maximally mixed state, which is a generalization of uniformity testing that I discussed before. And then this recent paper is about the generalization to generic sigma. So I want to, well, suggest reading this paper if you are interested in the topic. Especially the second one is it's very the techniques are elementary, and so it would be really insightful to have a look at it if you are interested in this problem, because the techniques could be used also in other settings. But this is not the bosonic cases, finite dimensional. So I hope you are already expert about continuous variable system and Gaussian states, because I will not go through all the definitions. Last week uh, I was at QIP and I said, okay, this moment is a bit embarrassing, because if you already know what a continuous variable system is and what a Gaussian state is, then you don't need this slide. If you don't know what it is, it will take all the talk to explain it properly. So I will give you this dangerously oversimplified analogy with what you know for sure. And okay, maybe now you don't need it, but just as a reminder, let me recall what we mean. So probability distribution on an infinite set, and also in some sense also the probability densities can be imagined as a kind of discretization or limit of the finite probability distribution on finite set, and then you take some kind of limit, of course with many caveats that I'm ignoring. Continuous variable systems, the simplest way to look at them is qubits with d equal to infinity. And Gaussian states can be imagined as the quantum generalization of Gaussian distribution. So apart from this, that you know way better than what I'm saying, what I want to stress is that for continuous variable states, we will care about their energy, their mean vector, and their covariance matrix. These will be the crucial quantities that we are going to use during this presentation. And also remember that Gaussian state is fully characterized, and this is the same also for classical distribution, as you perfect know. A Gaussian state is fully characterized by its mean vector and its covariance matrix, uniquely identified by them. So what about testing Gaussian states? So we will consider a tolerant testing, which means not only that we have this gray area that we need, as we saw in the classical example, but also that we may want to, and this is quite a reasonable request, we may want to test approximate Gaussianity. So we may want to accept also states which are epsilon a close to the set of Gaussian state. Both for Gaussian state and for this uh, epsilon a closed state, we want to say yes with high probability. While for states which are at least epsilon b far from the set of Gaussian state, we want to say no. And please keep remind that if we can always say epsilon, we can always decide to have epsilon a equal to 0, and therefore in that case we test exact Gaussianity. But this is a generalization that, for practical purposes, could also be interesting. So if you want to represent the acceptance probability, in the different areas. You want it to be smaller than delta in the purple area, then there will be a transition in the gray area. And then for Gaussian states or uh, epsilon a approximate Gaussian state, you want the acceptance probability to be at least 1 minus delta. So what are the approach, what is the approach that we are going to consider in this presentation? First, we need to understand the properties of the set that we are testing. So in particular, we are going to discuss its symmetries and also, as we already mentioned, its characterization, also in terms of mean, covariance, energy. Then there is a delicate topic, which is the choice of the notion of distance. We are going to choose the trace distance for operational reasons and also for technical reasons. Um, Olevo Hellstrom interpretation theorem in order to characterize the trace distance in terms of the acceptance probability in symmetric hypothesis testing. But in principle, we could use also other notions of distance. And in the end, maybe if I have time, I will mention the case of relative entropy of non-Gaussianity. Then we're going to use as technical tools the trace distance bounds that I'm going to state later. And it will be crucial to distinguish two regimes, one of testing pure Gaussianity, so Gaussianity with respect to the set of pure Gaussian states, and then mixed Gaussianity, so testing with respect to the set of arbitrary Gaussian states. So regarding pure Gaussianity, this is the setting. We fix epsilon A, epsilon B, failure probability, and we denote by GE the set of pure Gaussian state, with mean energy per mode at most at E. So an algorithm to perform this property testing task is successful whenever the following conditions are satisfied. So if we have a possibly mixed state ρ, which is epsilon A close to the set of pure Gaussian states, then the algorithm must accept this state with probability at least 1 minus delta. And if the state, on the contrary, is epsilon b far from GE, then the algorithm must reject the state. And in the gray area, as usual, we don't care about the answer of the algorithm. So the first approach is the symmetry. Um, so studying the symmetry of the problem might be a key tool, a key approach to understand the structure of the subset that we are testing, and therefore a key tool to design suitable tests. Let me give you a hint of the symmetry of Gaussian state, just starting in the fully classical setting. So suppose that you have a twice differentiable function f, and suppose also that it is integrable. So up to a normalization, if you take it to be positive, it could be a probability density. And suppose that this function, whenever you take two copies, is invariant under rotation of p divided by 4. So this is the equation identifying these rotation invariance properties under these angles. What can we say starting from this functional equation? Well, if you take the logarithm of the function on both sides of this equation, And then you take the derivative with respect to x and to y. Of course, these two terms will cancel because they depend either on x or on y. And so you will be left with this identity. And if you just simply do the computation, it's very easy to show that this is equivalent to say that um, the second derivative of the logarithm of f is constant, and therefore f is Gaussian. So symmetry implies this property. And if you think about it, any Gaussian function with zero mean has the property of being a rotational invariant. So what about the case of quantum states? So define u theta to be the rotation on functions on R to n, which is a way to represent two copies of our bosonic system. So using this identification, you can apply this rotation to two copies of pure states on our Hilbert space. And so this proposition um, characterizes the zero mean pure Gaussian states as follows. So requiring that these two copies of a given pure state are invariant under rotation for any arbitrary angle theta is equivalent to asking that these two copies are invariant under a rotation of a fixed theta. So you don't need to test all the rotation, you just need one theta, which is of course non-trivial. If you just swap the two copies, then of course this would hold in general. But you need just to test one theta, and one theta is enough. It's equivalent to say that psi is a pure Gaussian state with zero mean. So how do we implement this idea in our testing proper problem? So it's possible to prove, and I will not spend so much words on this because I wanted to go a bit more in detail on the learning approach, which is more related to the topic of this winter school. But it's also important to mention the symmetry approach. So if we take two copies of the state that we want to test, and we measure, so we perform a measurement, a projective measurement uh, in the rotation invariant subspace, the rotation invariant under all the angles theta, then a polynomial number of repetitions of this test with respect to the system size is sufficient to solve this property testing problem. So you just need to test several times whether this state, these two copies of the state belong to this rotation invariant subspace, and then you can tell in the end whether you can say with high probability that is at least epsilon A Gaussian. So the implementation for rotation invariant subspace in general could be challenging, but in principle we could simplify it uh, by taking auxiliary systems with a smaller dimension. For instance, here you want to perform, well, this looks like, if you're familiar with it, looks like the swap test. Here you want to test another symmetry, you want to test the rotation invariance when you have two copies, and so you prepare a superposition of the vectors 0, 1, 2, 3, up to 8. And then you perform this rotation, the test of these rotations. And in the end, you can measure whether it is invariant or not under multiples of pi divided by 4. And in principle, you could also simplify it just to testing whether it is invariant or not under pi 4, divided by 4. Of course, mm, the test will be more effective uh, if you consider arbitrary rotations. So there is this trade-off between implementation and um, number of copies that you need. But in any case, you would get a polynomial number of copies with respect to system size. And this approach, if you want to have a look at the paper, will be can also be generalized to non-zero mean state. Also, as I said, smaller auxiliary system or other kind of test like testing the generator of the rotations. But let me move now to the case of learning. So what time is it? Yes, okay. Good. Uh, so an important uh, characterization of pure Gaussian states is that whenever you consider their covariance matrix and you perform um, the symplectic decomposition of the diagonal of the covariance matrix, then the symplectic eigenvalues are all equal to 1. So are you familiar with this notion of symplectic eigenvalues? Have you already discussed it in the previous lectures?
Yes, maybe. Yes.
Okay, good. So just keep in mind that it's always possible to write the covariance matrix of a continuous variable system in a form which is given by a symplectic matrix, a diagonal matrix, and the elements of the diagonal are called symplectic eigenvalues, and then uh, the symplectic matrix again with a transpose. And so if and only if they are all equal to 1, then you have a pure Gaussian state. So what could be an algorithm according to you to test whether a state is a pure Gaussian state or not? Do you have any idea, any suggestion? Come on, don't be shy. I mean, it's not an exam. So what could you do, operationally speaking? So you know this characterization. You want to see if you are getting far or too far from this characterization. So what I would do is take these n copies of the state and to perform a measurement. And the measurement uh, is meant to determine an estimator of the covariance matrix. And then we should perform uh, then classically, because now you already used all the copies of the state, symplectic decomposition of this matrix and see whether uh, the largest symplectic eigenvalue is way far from 1, and in that case, one would expect the state not to be Gaussian, or sufficiently close to 1. So here we have an estimator, so even if we had a perfect pure Gaussian state, the estimator will have some statistical noise, so we will never get exactly one. But of course, we have some thresholds here. So, well, we need to tune these new thresholds in order to separate the two regions that we are interested in, so that if the largest estimated symplectic eigenvalue is larger than the threshold, we are outside the property testing region, the property region to be tested, and if it's smaller, we are inside. So in order to do that, I wanted to show you some technical tools that you, well, in principle, if you're going to do research in this topic, you might be interested in and you might need in some problems. So I wanted just to give you just a quick overview of the statements. So first of all, how do we learn the covariance matrix? Well, there exists a protocol which uses uh, a polynomial number of samples of any arbitrary n-mode quantum state with second moment of the energy upper bounded this way. Uh, and this protocol produces estimator of the covariance matrix of the state and also of the mean in case you need, with high probability up to an error epsilon, just using single copy measurement. So if you remember the algorithm that we discussed before for testing the symmetries, um, involved two states at the same time, which is not so challenging. We are not asking to have an arbitrary number of states to be tested at the same time. But of course, a single copy measurement it's even stronger. It's easier to test, of course. Um, then we are going to use some trace distance bounds uh, to
I
see.
have some question.
Yeah, sure.
You said we use single copy measurements. What if we
Yeah.
use multiple copy measurements, and will that be an advantage in this case?
So yes, good question. Since we already get a polynomial sample complexity, um, this well, if we just care about distinction between polynomial and exponential, this is not needed. If you
Uh,
want to find the optimal sample complexity,
yes.
I'm not aware about results in the literature. You
Uh,
should consider arbitrary measurements, but then maybe you can theoretically prove that um, it
so
can be
the
improved,
trade-off,
but then. Mm.
is not proved.
I'm not, no, I don't think so. I'm not aware
Uh,
of any results. For sure, in this paper that I'm reporting here, they consider just the single copy measurement setting. Yeah.
okay, thank you.
But of course, it would be interesting to study this trade-off if it's not already known in the literature. Um, then, okay, in the end, I will also mention the case of arbitrary measurements, but for another setting, for the setting of mixed Gaussian state. Mm. Then trace distance bounds. The trace distance between two Gaussian states for which you know the exact mean and covariance can be upper bounded in terms of the distance between the covariance matrices and the mean vectors. And similarly, if you have an arbitrary state, sigma, which does not need to be Gaussian, and a pure Gaussian state, then you can provide another upper bound. You can also provide lower bounds, either in the case of Gaussian states where the mean or the covariance are exactly known, or for arbitrary Gaussian states. No, sorry, for arbitrary states which do not need to be Gaussian and, well, for which the mean and the covariance are different. Finally, we will need some perturbation bounds. So when you take two covariance matrices, in principle, they may not commute. They may not be diagonal at the same time. And when you perform the symplectic diagonalization, you may want to compare their symplectic eigenvalues in terms of the distance between these two matrices. And what you can do is to use this lemma and to upper bound the distance between the symplectic eigenvalues arranged in decreasing order in terms of the norm of the difference of the covariance matrices. So, okay, we have all these bounds. We have a clear task that we want to perform. How do we combine them? Which one do we need? So, you see, when you have all these tools and you want to solve a problem in this setting, you always need to really try and see what you actually need according to the specific problem. So I just wanted to give you a brief recap of all these tools and now to show how they will be applied in the proof. So the idea is that we want to uh, give an estimation of this distance. The unknown state that we want to test, of course, has a mean and covariance, which are not known. But theoretically, we could define a state psi bar, which is a pure Gaussian state with the same mean, and the covariance, which is given exactly by the same form of V, but you replace the diagonal matrix with the symplectic eigenvalues with the identity. So you set all the symplectic eigenvalues to be 1. And this is a pure Gaussian state. So in principle, you can use it as a guess, an ansatz for the closest state in this set. And in general, it will not be the closest, but at least you can upper bound this distance in terms of the distance between rho and psi bar. Of course, well, first of all, okay, let's suppose that we know mean and covariance, and we want to upper bound this distance. So it's easy to prove that in the end, this upper bound will just reduce to this sum of the difference between the symplectic eigenvalues of V and 1, which will be the case of a pure Gaussian state. And how do you prove that? You write down explicitly the state psi bar as a Gaussian state, and then you use, first of all, to estimate the trace distance Fuchs van der Graaf to compare it with the fidelity, which is written this way for a pure state and a mixed state. And you just write down the state psi bar. Here you use this identity, or to be precise, this operator inequality. The identity operator minus the projector onto the Fock state 0 is smaller than the number operator. Number operator, you remember, it's it's related to the energies, the sum of A dagger A over all the bosonic modes. And then you just perform these computations by writing explicitly this n hat, the number operator, and you will find out that you reduce to the trace of the diagonal matrix of the symplectic decomposition of V minus identity, and in the end, that's how you get this upper bound. But of course, when we perform this measurement, we will get an estimator of the covariance matrix, and so an estimator of the symplectic eigenvalues. And since we will have statistical noise due to the finite number of samples, we'll have to take into account the fact that rho tilde is not rho. So if you add this noise to the upper bound, then you will get this expression. And the key tool is just to use that the two covariance matrices are close. So also the symplectic eigenvalues will be close, and therefore you can do a sort of triangle inequality to compare them. So this is the upper bound on this distance. What about the lower bound? Well, you can proceed similarly. Here you use the lower bound between two arbitrary states in terms of the covariance matrix. And then you move from the covariance matrix to the symplectic eigenvalues, again by using this inequality. And finally, in order to take into account the statistical noise, you use again this perturbation argument to compare the symplectic eigenvalues of the original covariance matrix and of the estimator of the covariance matrix. Okay, now the last step is to define a threshold, and this it's not a particularly difficult computation, so I will not show you the details, but just the idea is that you want to define this threshold so that whenever nu tilde max is smaller than the threshold, then you will have that the estimation of the distance will be at most epsilon b, and so we will be either in the gray area or in the property region. While whenever this nu tilde max is larger than nu threshold, then the distance will be at least epsilon a, and so we will be either in the gray area or in the region which does not have the property. So in the end, the theorem can be phrased like this. If rho is a possibly mixed state satisfying the second moment energy bound, and if epsilon A and epsilon B are chosen in order to satisfy this inequality, then single copy measurement and a polynomial number of copies of rho are sufficient to solve this property testing problem. So you may wonder why we have this ugly inequality. Why is this needed? Well, if we go back to the previous slide, the reason might be clear. The fact is that in order to make these two inequality imply these two inequality at the same time and for arbitrary states, then you really need a bound. You cannot take epsilon b and epsilon a arbitrarily close. Otherwise, due to the specific form of these upper and lower bounds, you will not be able to ensure the two conditions at the same time. But of course, if you set epsilon a equal to 0, which is exact testing of Gaussian state, then it will be fine. the condition is satisfied. Okay, I was planning to give you a 5 minutes break before discussing the mixed case, but I see that a few minutes are left. So let me know, what do you want to do? Do you prefer me to skip the break and give you more details on the mixed case scenario, or do you want a break, some time for questions, and then I will just give a general idea for the mixed case? Let me know what you prefer.
Let's skip the break.
Mhm. Are you all fine with it?
Great.
Yeah, okay. So when you consider the set of mixed Gaussian states to be tested, then you just take the previous slide and you replace GE by GE mixed, and then everything is the same, apparently. Uh, the fact is that in this case, theorem, well, if you have the second moment of the energy to be constrained, and you have epsilon A and epsilon B to be at most 1 over a polynomial that I'm not writing here in terms of n and e, so polynomially bounded, then performing this property testing task, we require at least an exponential number of samples, even if you take entangled measurement. So you, if you have a quantum memory, if you don't restrict to single copy measurements, then you will need in any case an exponential number of samples. So this problem is fundamentally hard to solve. And the strategy is that we take the original identity testing problem in the classical setting, and we use the Gaussianity test as a subroutine of a strategy which can identify whether we are observing NIAD samples of Q or NIAD samples of P, which is at least epsilon far. So more precisely, we take the samples of this random variable, we use them to produce a state to be tested, NIAD state to be tested. We perform a pre-processing of this state, which requires just a polynomial number of copies, and then we perform the Gaussianity test. And in the end, using the hardness of this testing for a suitable Q, we can lower bound the sample complexity of the Gaussianity test, because this black box solves this problem. So the number of copies that this black box is using is lower bounded by the theorems regarding this classical problem. And so we can lower bound also the number of copies that used by the Gaussianity test. More precisely, how does this theorem work more in detail? So the way to phrase it, the way we are going to use it is the following one. Whenever we consider this Q, there exists a family of probability distribution depending on Q and on epsilon, which have the following properties. First of all, if P is a probability distribution is in this family, then P has the following form. It's just a perturbation of Q. You see, it's just Qi with some small noise. So it's almost Qi. Then you can add or remove some for epsilon weight to it as a multiplicative term. And then this is just the normalization. So it will be very, if you consider the plot of the probability distribution, it will be very close with some noise. Then all the P in this family will be at least epsilon far from Q. And please note, this is not the case for any generic P of this form. So We are not taking all the P that have this form for any arbitrary Z of this form. No, we are just selecting some P because only some of them will be epsilon far. But the number of elements in this family is large enough so that testing whether a distribution P is Q or belongs to this family has a sample complexity which scales as I showed before in the previous slide. So this family is exactly the family of uh, adversary probability distribution, which might be uh, wrongly guessed to be Q. Uh, and which are at least epsilon far from Q. So the first step of the proof is that we want to encode P, any generic probability distribution, P on n copies of the natural numbers, into a bosonic state. How do you do that? Well, you just define it like this. This will be the coefficients in the Fock base. So it's Fock diagonal. And if you consider this specific distribution Q of K, and it's just a multidimensional geometric distribution, you see, and it's easy to compute that rho Q is given by NIID copies of the thermal state tau nu, which is a simple example of a Gaussian state. So in principle, rho P is non-Gaussian, but whenever you choose Q, the specific Q, then you get a Gaussian state. And in order to apply the trace distance bounds, we always need an energy constraint. So we need to make sure that the energy of this rho Q, the second moment of the energy, is suitably upper bounded. In order to do that, we need to make a specific choice of nu. So this is just a simple computation. You write down the definition of the energy, you expand all the terms, and you will find out that using this specific state, you will get this identity. And so you set nu so that it satisfies this equality. And you can see that nu will be asymptotically of the order of the energy. So that, let's keep in mind this equality. So that, first of all, the second moment of the energy will be bounded as we want, according to the hypothesis of the trace, trace distance bounds for rho Q. Whenever we take any element of the family defined by this Q in the classical theorem, the elements of the family will have this form, a specific form, so they will be a perturbation of Q. And therefore, we can upper bound their energy by the second moment of the energy by linearity by taking the largest numerator, which is 1 plus for epsilon, and the smallest denominator, 1 minus for epsilon. And then what you get here, just get Q. And so you get, instead of rho P, you get rho Q up to this prefactor. And so you see this choice in blue is exactly the one which ensures that also the perturbed states using the probability distribution P will have the same upper bound on the energy. And so we will be allowed to use the trace distance bounds also for these states. And of course, using the properties of these families and the fact that the embedding in the quantum system is an isometry, these states will be at least epsilon far, because P and Q are at least epsilon far. So let's save here all these inequalities, and let's embed the classical problem of property testing into a quantum system. So the idea is that we take the samples of this random variable, and whenever we sample xi equal to this small xi, then we prepare the following state on our system. So the state that we obtain in the quantum system is just the probability of getting x1, x2, xn total number of copies, which multiplies, of course, the state that we are preparing. So this is just classical description of uncertainty when having quantum states. And it's really easy to be factored in this way. So we are just preparing n copies and total copies of rho p. Now, first step, the one requiring, as I said before, it was the pre-processing, a polynomial number of copies of the state is the following one. We make, again, an estimation of the covariance matrix of rho p using just a limited number of samples of rho, not all of them. We produce an estimator which is epsilon v close to the actual covariance matrix of rho p, and we choose epsilon v in terms of epsilon, the distance that is appearing here. As a consequence, for this choice of epsilon v, the number of copies that we are using for this first test is polynomial in the number of in this number of modes, so the size of the system. Now, if it turns out that the estimator is epsilon v far from vq, so the covariance matrix that we would have for the probability distribution q, then it's easy to lower bound by a reverse triangle inequality the distance between vp and vq. And this distance is strictly positive. So this means that the distance between p and q, which is the distance between rho p and rho q, remember that it is an isometry, is positive. Because if this was a lower bound, if two states, arbitrary state, have a strictly positive difference of the covariance matrix, the infinity norm of the covariance matrix, then they have this lower bound. So we can state that we are not observing Q because there is a positive distance. And so we are not making a mistake. This is correct. What about the remaining samples? Sorry if I'm 5 minutes late, but I'm going to finish now. Now, okay, if the estimator was larger than epsilon, was for at least epsilon v from the expected covariance matrix when you have Q, then, okay, we already said, no, it cannot be Q. So we already gave an answer to this testing problem. But what if they are close? So they look the same. Shall we say that it's Q? Well, it depends. We now run the Gaussianity test, and according to the outcome of the Gaussianity test, so either rho p is epsilon a close to the set of mixed Gaussian state, or it's epsilon b far from the set of Gaussian state, then according to the outcome of the Gaussianity test, we state Q or P as the answer to this testing problem. And why can we say that this would correctly answer this testing problem with high probability? Well, first of all, because suppose that Q was indeed the actual probability distribution of the random variables here, then of course rho p is rho q. And rho q is Gaussian, so this distance is 0. So the Gaussianity test will always accept the Gaussianity of rho q if rho q, since rho q is Gaussian. So this will be the right answer. But what about the case of having the random variables here distributed as a p which is at least epsilon far from q? Is it true that in this case the Gaussianity test will always say that the state rho p is at least epsilon b far from the set of Gaussian state? Because if this is the case, then we will always give the right answer, p. And if this is the case, then the number of samples used by the Gaussian testing will be the total number minus the number already used for the covariance testing. And the total number is the classical theorem that you remember, classical lower bound, and then here we use the achievability protocol, which is polynomial. But you see, this first term is exponential in the number of modes. And nu, if you remember, scaled with the energy, so in the end we will have a sample complexity which is exponentially in the number of modes. So the last thing to be proved is that indeed if here we had p far from q, then the Gaussianity test will reject the hypothesis of being close to the set of Gaussian state. So how do we do that? We prove this reversed implication. If we are not epsilon b close to the set, if we are epsilon b close to the set of Gaussian state, then we are epsilon close to q. It's just the reverse version of this. So how do we do that? We use the isometry properties, first of all. Then we compare the state rho p with its Gaussianification. The Gaussianification is just taking a state, taking its mean vector, its covariance matrix, and considering the Gaussian state which has the same mean vector and the same covariance matrix, which in general will be different from rho p. And so you do this triangle inequality. You use an upper bound between a state and this Gaussianification in terms of their trace distance. Now you use that this trace distance it is at most epsilon b, because we are assuming that HP does not hold, so that we are at the most epsilon b far from the set of Gaussian state. And here, for this quantity, we are comparing two Gaussian states, the Gaussianification and rho q, which, as I said, is Gaussian. And so we can use an upper bound in Gaussian state from our toolbox. And this concludes the proof. Because if you perform all the computations and you use the assumption that here we have a distance at most epsilon v, you just have to replace everything in this bound and choose epsilon to be written in terms of epsilon b and this constant, then you will get exactly that this is smaller than epsilon. So, okay, this is the end of the lecture. So we discussed two protocols to test pure Gaussianity with a polynomial number of copies of rho, one based on symmetry, the other one based on learning. We proved the hardness of testing mixed Gaussianity, even if you have access to a quantum memory. And of course, there are still many open questions, such as what is the optimal sample complexity? How do we improve the hardness result, not requiring that epsilon b is 1, at most 1, divided by a polynomial on the system size, but it's just smaller than a constant. And I mentioned other notion of distance to be used for property testing problems. And indeed, if you consider the, the relative entropy of non-Gaussianity, then you can prove an hardness theorem with epsilon be constant. And this is in the end of our paper. So, well, I know that I was a bit fast in the last part. I hope that at least the idea was clear. If you have any question, please feel free to ask now or to send me emails or whatever you want. And thank you so much for your attention.
Great. Thank you very much for a nice lecture. And I think there is one question in the chat box.
Sorry, there is?
Yeah, I think there is one question in the chat box here.
I don't see the chat. Let me see. How do I see the chat? Sorry, I don't know how to open the chat.
Okay, maybe Songhyun, can you read your questions?
Yes, please. Maybe. Okay, maybe I can see it now. Let's go for step one. After confirming that two distributions have which of a covariance matrix. Yes, of course. Great question. We struggled a lot in this regarding this problem. So please let me know if I'm correctly understanding your question, because if it's what I think, then it's really interesting. So you say, okay, if the two covariance matrices are far from each other, then okay, we say, well, then it's not Q. It cannot be Q. It must be something else that produced this state. And that's fine to reject Q. But if they are close, one could say, okay, they are close, so why cannot we conclude that it's Q, right? Is this the question? Am I right?
Yes, right. That's right.
Okay, perfect. So this is quite puzzling, and the problem is this weird geometry of Gaussian states. So the fact that two covariance matrices um, are close in this embedding here, it's not sufficient in principle to conclude. So there might be some p which are epsilon far in trace distance, but for which the covariance matrices are still close according to this epsilon v. Well, of course, if you choose epsilon v to be exponentially close, exponentially small, and I mean, then of course you might be, I don't know, we should make the computation, but you might have stronger guarantees. But then you will have a bottleneck here to choose epsilon too small. You may have an exponential number of copies here. But this, well, I don't remember all the computation that we did. But the fact is this one. So you can have a close probability distribution to Q and still, sorry, far probability distribution for Q, epsilon far probability distribution from Q, and still have covariance matrices which are close. So that's why you need to perform a Gaussianity test. I hope this answers your question. I mean, the way to see it is just to try and do the computations step by step. And with this embedding, we will see that it's not straightforward to.
I think I can't understand it. Can I have you one more small question? Like,
Yeah, sure.
and for me, first, I'm not a really researcher who study mm, quantum information. So while I see the slides and step one and step two, I just kind of wanted to match it with my familiar domain, which is finance, like distribution and finance samples, covariance, and these things. We can just convert it to, for me, I just convert it to like return distribution, historical price data, and for covariance metrics. But do you think like is this approach could be really useful for the research, not just my understanding? Um, I'm not sure like how this field really works. So what is your opinion? Can I apply this to finance, or is it not really connected topics?
So you say to finance?
Mm-hmm.
Okay, I'm not familiar with that topic. So to finite no, sorry, I'm not understanding. You mean to finite dimensional?
Finance.
Finance. Okay, no. I was in doubt if it was finance or finance, because if the question was about finite dimensional, then I could say yes, there's a similar strategy. If it's finance, I don't know how it works and what are the techniques and the problems used there. So uh, I don't know. Honestly, I don't know how to.
Thank you.
Are there any other questions from audience here? Maybe I have one small question. Can we
Yeah, sure.
use some, can you use this property testing subroutine to maybe to obtain some agnostic learning algorithms, or do you have any other suggestions?
Sorry, you want to use this property
Yeah,
testing
maybe
too?
can we use this property testing to obtain some agnostic learning protocols?
On what do you want to learn
Ah,
specifically?
um,
Give me an example of what
yeah,
you.
maybe agnostic learning for Gaussian state.
So what? Hmm. So okay, more precisely, what do you mean by agnostic learning? So what you are not assuming,
Mhm.
and
So
and what do
maybe
you
can
want to
we
learn?
learn best approximation of given quantum state as Gaussian states?
Ah, okay. So given a continuous variable state, you want to know the best Gaussian approximation.
Right, exactly. Right,
Well, this is hard even analytically.
right.
Because I mean, okay. Good question, great question. So it will be okay. No, this question is very relevant. Also, apart from learning, theoretically speaking, so the reason why in the end we get this weird constraint here, you see, we request this polynomial constraint on epsilon b is exactly related to your question. Uh, because here, when we do this upper bound, this triangle inequality, we are using the Gaussianification of a state for a comparison with rho p and rho q. And this is not in general a good ansatz. It's not in general a good choice, because then you get this coefficient here which scales with system size and so. But in the end, this is the reason why we need the constraint on epsilon b, because we want this epsilon to be at most 1. So epsilon b will be at most 1 divided by this coefficient. And so there is the moment where this constraint appears. Um, So if we knew, given a state, the characterization of the closest Gaussian state, then here we would do a smarter ansatz. But we don't know. It's really hard to characterize the closest Gaussian state to a given continuous variable state. So this is not the case when you consider the relative entropy from Gaussianity. When you take the relative entropy of non-Gaussianity, the minimizer here in the second argument is exactly the Gaussianification. And this is an exercise that you can do. You can try to prove it. Should not be too hard. So that's why in this case we can achieve a statement of hardness with epsilon b constant, because we don't have these, or at least this ansatz is good here. So what you can do, a learning protocol that you can do for what you were interested in is take a state, perform the learning of mean and covariance, as I said before, with a polynomial number of measurements, and then you can consider its Gaussianification. But this will not be the closest state. It will be close. It will be close somehow. Well, I mean, you can use these bounds to see how close it might be. But yeah, in general, it will not be the closest. So I don't know. It's an interesting question. I don't know if operationally it's possible to find this with a procedure and not analytically. I have no idea at the moment. But you see, it's a really complicated geometry to study.
Great. So for today, if students don't have any more questions, maybe we can finish this after two. Any questions?